Okay, here we shall do about the applications of Ampere's second law to find the magnetic field due to a solenoid. Alright, so we have seen before in the previous video that the current which is entering through the solenoid are indicated by cross with a circle, and the current leaving the solenoid it is indicated by a dot with a circle. So one dot, one cross mean one turns of the solenoid. If we have another cross, it means two turns. So how many dot and how many cross are there? Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in my example, in this figure, we have considered 13 numbers of turns of the solenoid, which means 13 turns of the copper wire. Alright. But actually, in practical case, you may have more than 13 number of turns. Not just 13, it may be more than 13. But in my example, right, as indicated in the figure, because one dot and one cross mean one turn of the solenoid, so it means 13 turns in this case. Alright, so now I will consider this is a long solenoid. Okay, and this long solenoid here, let's say it carries a current I. Okay, so what is the current in the solenoid? Let's say it is I. So it's difficult for me. Again, I have to draw like this. So this is the current I which is entering the solenoid. Okay, so I want to find out what is the magnetic field due to this solenoid. So to find the magnetic field due to the solenoid, what I have to do is, because according to Ampere's second law, that magnetic field it is actually should be surrounded by a closed loop. So look here, these are the turns of the solenoid. Now if I consider this is a closed loop, can I do this? Yes. Why I call a closed loop? Because this loop here, it is actually enclosed. Like I have these are the turns. Then if I draw a loop, like a rectangular loop, like this, up, like this. So this is my closed loop. That means this closed loop, it is actually, enclosed these turns. Okay. So it is difficult for me to show that here because actually we need a three-dimensional picture for that. But anyway, you have to think about it. All right. Okay. So suppose this is my closed loop. This is my closed rectangular loop. And I will name this closed rectangular loop as A, B, C, D. Okay. All right. Now you know that inside the solenoid, the magnetic field, right, it is directed from left to right. So this is the directions of the magnetic field. Okay, now I will choose this length AB as L. What is the length of this closed loop? L. And what is the breadth? Let's say it is small b. Okay, now according to Ampere's second law, the line integral of the magnetic field over the closed loop, that is B dot dl integration, is equals to mu naught times the total current enclosed by the loop. Okay, all right. Now this B dot dl, which is the line integral over this closed loop A, B, C, D, I can split this integration into four parts. Okay, so this line integral B dot dl, right, it means the integrations from A to B. So from A, I will write in this way, the line integral B dot dl, it is equals to the integrations from A to B. B dot dl plus integrations from B to C, B dot dl plus integration from C to D, B dot dl plus integrations from D to A, integrations of small b, small, again I made a mistake, this is from D to A, B dot dl. Okay, so in this way you split this line integral of a magnetic field over a closed loop. Okay, now what is this integrations from B to C and D to C? Now look at these two. The integrations of the line integral from B to C and C to D. From B to C, you are going from B to C. So you are going up. Whereas the magnetic field inside the solenoid, it is directed in this way. So that means if you consider a small length dl over this sides BC, then the angle between dl and the magnetic field will be 90 degree. So as you know, B dot dl means B dl cos theta. But along the path BC, theta is 90 degree. So cos 90 is 0, so everything will be 0. So it means here that along the path CD, this integration B dot dl will be 0. Similarly, along the path, BC and then sorry, made a mistake. This is DA. From D to A, right? If you consider any small elemental length, DL, then this elemental length DL, right, it will points down, whereas magnetic field is going like this. So again the angle between B and DL is 90. So in that case, this integration also will be 0. Okay. Now, look at this. Integrations along the path CD. So if you look at this part CD, this CD, it is actually outside the solenoid. So outside the solenoid, we have seen before that magnetic field is 0. So when B is 0, because B dot dl can be written as B dl cos theta. But if B is 0, then everything will be 0. So it means this integration along the path CD also will be 0. So hence, the only integration which is left uncancelled here, it is along the path AB. This AB, it is inside the solenoid. So therefore, I will write B dot dl, it is equals to just the integrations along the path from A to B, B dot dl, which means, okay, integrations from A to B, your B dot dl can be written as B dl cos theta. And what is the angle theta in this case? The angle theta, which is the angle between B and DL along this part AB. So along the part AB, both, if you consider a small element DL, so both B and DL makes an angle 0 degree. So if you put theta equals 0, then cos 0 is 1. So 1 times BDL will be just BDL. Okay, I'll drop this. Again, if you further extend this, I will write integrations from A to B. And because, this magnetic field B along the path AB, that means inside the solenoid. So inside the solenoid, what happens to the magnetic field? The magnetic field is uniform. So if it is uniform, then I'll take this B outside the integration sign and I will integrate only just dl. Okay. Now, this integration B dot dl, it becomes B times the integrations from A to B. So from A to B, if you integrate, you will get the total length L. So times L. So this is my equation number 1. Okay. Now, Again, look at this equation 1. The integrations of B dot dl is equals to mu naught times the current enclosed by the loop. Okay. So here, how much is the total current which is enclosed by the loop? Okay. So in my example, I have chosen how many turns? 1, 2, 3, 4, 5, 6, 7, 8. There are there are 8 number of turns of the loop. Okay, but let us say that instead of 8, suppose I don't know how many turns I have chosen. Let's say there are n number of turns that enclose this loop A, B, C, D. So if n is the number of turns which enclose the loop A, B, C, D, okay, per unit length, per unit length. When I say per unit length mean, let's say the number of turns per 1 centimeter of the loop or per 1 meter of the loop, it is n. So if n is the number of turns, then what is the total number of turns over this length L? How many number of turns, right, you have taken over this length L? So over the length L, the total number of turns will be over length L, number of turns will be n times L. Which means number of turns per unit length multiplied with the length of the solenoid over the length of the loop, you can say it is equals to the total number of turns. So, but look here, because each turns of the solenoid carries a current I. If I consider 3 turns, the current will be 3I. If I consider 4 number of turns over this closed loop, then my current will be 4I. Okay? But in this case, what is my total number of turns over this closed part A, B, C, D? My total number of turns it is NL. So if NL is the total number of turns, then it means the total current enclosed by this closed part A, B, C, D will be NL, number of turns, times the current enclosed by that closed loop. So therefore, okay, this BL here, which is equals to mu naught times summations of I, comparing these two equation 1 and equation 2, left hand sides are equal. So it means BL is equals to mu naught times the total current enclosed by the loop. Or BL is equals to mu naught. What is the total current enclosed by this loop A, B, C, D? So here we have seen it is equals to total number of turns over the length L times the current in each turn, that is I. Or this L from the left, L from the right can be cancelled, so just B will be equals to mu naught N I. Okay. So this is the expressions of the magnetic field at the center of a solenoid carrying a current I. So please note down this equation. Okay. Now, suppose this is my solenoid. This is my solenoid. Inside it is empty. If it is empty, then I call this solenoid as an air core solenoid. Okay. So when the space inside it is empty, then we call that solenoid as air core solenoid. But now, if I insert, let's say, a material, I insert like this, a material which is having a relative permeability mu r. My relative permeability is mu r. So if you insert such a material having a relative permeability mu r, then this magnetic field inside that, now I will call no more air core solenoid, but I will call a solenoid with a material inside. So in that case, the expressions of the magnetic field inside a solenoid with you know with an iron core, it becomes B equal mu naught mu r n I. So this is the expressions of the magnetic field when an iron core it is inserted inside the solenoid. Okay, so this is my equation number 4. All right. So again, another point to be noted here is this: near the ends of an air core solenoid, that means at this end or at this end, the magnetic field at these ends of the air core solenoid, because we have seen right from equation 3, the magnetic field due to an air core solenoid is equals to mu naught n I. But near the ends of the air core solenoid, near the ends, the magnetic field is equals to half of this. That means half mu naught n I. So this is the expressions of the magnetic field near the ends of the air core solenoid. Right? So I hope you have understood about this topic regarding the applications of Ampere's second law to find a magnetic field due to a air core solenoid.